Okay, let's continue. So first of all, belated Diwali wishes. So hopefully you guys bursted crackers. Hopefully through this course you will learn how to not burst ICs. That's the whole thought. So anyway, start off from where we left, we looked at ways to stabilize our two-stage OTA. We looked at two ideas. One was the Miller compensation, where the idea is to make sure that the open loop poles are kept far apart, and that you do it like this. So let's say if I draw, this is the first stage. Let's say this is the second stage. So I'll draw the conductance capacitance here. So similarly, I'll draw the conductance capacitance here. So let's say this is GM1, GM2. So what do you do in Miller compensation to compensate this? Yeah, capacitor across this second stage. And we also know how to take care of the right of plane 0 due to this. So I leave that, right? So here, just to make sure you remember, what is the unity gain frequency approximately? I mean, okay, it's remember it's GM1 by CC. The feedback factor comes if you look at the unity loop gain frequency, right? So here I'm just looking at the unity gain frequency. So GM1 by CC. And what about the second pole approximately? GM2 by, let's say I call this as CL prime and GL prime. So roughly it is GM2 by CL prime. And this must be stable and must have a good phase margin. What can you say about second pole with respect to the omega u? This should be much farther than the unity gain frequency, right? That's something we know. Similarly, we also saw about feed-forward compensation. So there, the idea is you add an left half plane 0 to sort of compensate it. So I'll not show it, you just do it. Okay. So now let us say you have designed this. I'll take Miller for example. So what is the DC gain of this structure? GM1 by G1. Let's say this is G1 times GM2 by GL prime. Yeah. So let us say now you find that the DC gain you get here is not sufficient with a two-stage OTA. So what can you do? Yeah, I mean, let's say, I mean, it's like adding coaches and coaches to a train. You keep adding one more extra stage here. Now, of course, a two-stage OTA itself was sort of not very stable when you put it in negative feedback. Now, if you have a three-stage OTA, if you put it in feedback, that will also be unstable. So we have to compensate that also, right? And as of now, what are the techniques we know for compensation? Miller and Feedforward. So you should probably use one of them or combination of them, right? So let us say you have a two-stage Miller compensated op-amp. Let us say I want to make a three-stage Miller compensated op-amp. What do you think might be a systematic way to derive a three-stage Miller OTA from this two-stage Miller OTA? People who learn programming, maybe. I mean, so this is a two-stage OTA. I want to make it a three-stage OTA, and I want to make sure it is, hopefully it is stable. What might be a systematic way to get a stable three-stage Miller OTA? Sorry? Yeah, but yeah, I mean, you probably have to add one more stage and something you have to do. But is there a systematic way to get it? I mean, in programming, what do you do in recursion? Yeah, the idea is now you have a two-stage OTA, just like in recursion, where you want to do where you want to keep doing things, recursively. You replace this by another two-stage OTA, right? If you replace this by another two-stage OTA, that's a three-stage OTA, and that's obviously will be stable because you are going to replace this by another stable OTA. The idea clear? So we can try that. So let me see if I can copy paste this. Okay, I don't want background music in my class. So I'll keep the same color coding. So this is the first stage. I'll draw the this is the Miller capacitor for this. Now the thought process is I'm going to replace this fellow by another two-stage Miller OTA. So I'll draw in the same color so that it's clear. So this is, let us say, the first stage. Too much. Maybe I'll give more space. And second stage. Right. So let me call this GM2 and GM3. So this is basically GL prime and CL prime. And here you have another conductance capacitance. Okay. Now this is a two-stage OTA. To compensate this, what should we do? Capacitor across which? GM3. Very good. So I'll basically go and put another capacitor here. And you have the other capacitor here. Okay. So let me call this CC1, CC2 to differentiate them. Now this is how a three-stage Miller OTA look like. And of course, if you exactly want to know the stability conditions, so you have no other choice, have to actually derive the third order cubic equation, make some approximations about the poles and sort of do it. But I'll just give a qualitative feel for the stability conditions. So for that, let's look at the two-stage OTA once. Here we already established that my second pole must be greater than omega u, correct? And second pole is roughly GM2 by CL prime, correct? Now let us say I take only the second stage here. Let's say I take this separately. Now this fellow alone is a single stage OTA. What can you say about the omega u for this structure? It's a first order system. So how do you approximate the unity gain frequency? Yeah, I mean DC gain times the first pole, how much will that come out as? GM2 by CL prime, right? This one. So which means I can think of it this way. So this fellow is essentially my omega u, I'll say, for the inner stage. That is this fellow. Seems like the inner stage should have a omega u, but that should be greater than the omega u for the outer stage. So this is basically the omega u for the overall circuit, which is the outer stage. So this is another way to interpret the stability condition, that in Miller compensation, we try to make sure that the outer loop is slower than the inner loop, or vice versa, inner loop is acting much faster than the outer loop. Is that okay? That's the other way to interpret the same condition. So now we can try to extend this to the three-stage structure. So here you see I have one inner stage, one outer stage, and overall outer stage, correct? Which means this is the innermost one. This should be faster than this fellow. This should in turn be faster than this overall structure. Does that make sense? So now we can tell me what is the omega u for the innermost stage, this alone. So the innermost stage is the last stage, which is GM3 by CL prime. This should be greater than the omega u for, let us say, this stage, outer stage. What is the omega u for this structure? This is a two-stage Miller compensated OTA, GM2 by CC2. Clear? This should be greater than GM2 by CC2. This should in turn be greater than the omega u for the outermost stage. How much is that? I'll maybe color code this. So this I light in yellow. This is GM2 by CC2. This should in turn be greater than GM1 by CC1. Is that clear? So the inner stage is this fellow. This is basically a single stage OTA, GM3 by CL prime. The outer stage just adjacent to it is a two-stage Miller OTA. So its omega u is the first stage GM, which is GM2 by the Miller cap CC2. And the outermost stage is basically this fellow. So this is, you can think of it as another two-stage OTA where this is can be taken assumed to be a black box. So this is GM1 by CC1. Now what the exact phase margin will depend on how far apart these are, and that's not very trivial to do. For the sake of time, I will not do it. If you want, you can derive it yourself or refer to textbooks. And of course, anytime you come up with something new, I say you should always give it a name. And the name this is called is nested Miller compensation for obvious reasons. Just like how in coding have nested loops, similar structure. Okay. So similarly, now if you want to make a 4-stage OTA, you can basically extend it. Should not be a difficult task. Right. So this is basically Miller, but we also know another trick in our sleeves. We have another trick in our sleeves, which is feed-forward compensation. Let's try to do the same and get a 3-stage feed-forward. So I'll quickly draw a 2-stage. So this is the, I'll not draw the signs. I hope you guys can figure it out. This is GM1, GM2. Let me draw. So this is GM2. And I know that for compensating, what will I do in feed forward? Yeah, how do I add the left half plane 0? Yeah, we add another GM in parallel to this. Again, the idea is if you just have these two, the 2-stage structure, we have parasitic capacitors due to both of them. We'll have a lot of delay. Now, when you introduce this path, this is bypassing the parasitic capacitor here. So you get a faster response. So that way you kind of counter the delay in the feedback loop. That's the idea. Right? So now we can do the same thing. We can replace, to get a 3-stage feed-forward OTA, all I'll do is replace this second stage by another 2-stage feed-forward OTA. So if I do that, I'll just show it very briefly. This, let us say, GM1. So I'll have, let us say, GM2. This I'm replacing with another feed-forward structure. Okay. So I have replaced this here. Now, of course, I should have this feed-forward path also. So that will come here. Now the exact signs of the GM, I will give it as an exercise for you to work out. Again, it should be in such a way that you get a left half plane 0 and not a right half plane 0. So in a 2-stage feed-forward OTA, how many poles we had? We had 2 poles and 1 0. So here, how many poles do you think we'll have? We'll have 3 poles. And how many zeros do you think we should be having here? 2. Why? Sorry? Yeah, 2 paths. And also remember that if I want to have a stable behavior around the unity loop gain frequency, how should I be behaving? First order system. So I have a third order behavior to start with. To get a first order system eventually, I should be introducing 2 left half plane zeros before I hit my omega u. Right? Before the unity gain frequency, I should basically introduce the 2 zeros so that I have the first order behavior. Right? So if I were to very briefly sketch the magnitude plot, let's say 1 pole, 2 pole, 3 pole, and then I have 2 zeros, something like this. So let us say pole 1, pole 2, pole 3. This is Z1, Z2. And in general, if you have, let us say, a total of NP poles, how many zeros I should have? I should have NP minus 1 zeros to get the feed forward compensation. Now that is with that way you can extend it further. Now again, it is not necessary that, here see, when we came to the 3-stage feed forward OTA, we replace a second stage by another 2-stage feed forward OTA. But is there some other 2-stage OTA that I know? Miller. So basically you can replace the second stage here by a 2-stage Miller OTA also. That's also fine. So that gives rise to more combinations. So maybe I'll just sketch it very briefly. So which means you will have something like this. So I have one stage here, one more stage here, and basically in here. Now in addition to this, you can even introduce another, feed forward path, fine. Basically here I'm doing both Miller and feed forward at the same time, right? So now you can play around combinations of everything till you get the required test match. And in practice, typically 2-stage and 3-stage OTS are common. 4-stage sometimes we use, and beyond that it's 4-stage itself is, I'll say, sometimes rarely used, but beyond that no one. Because by then we get the required DC gain, and after 4 stages the stabilization also becomes very tricky, so no one attempts to do it. So now one more point I wanted to make, so I'll take, we'll do this. But any questions so far? Okay. Fine. So let me just do one more thing. So far, right? So let me just draw it at a block level. So this is the op-amp that we have been trying to design. So in all our frequency, response or stability calculations, we have accounted for all the parasitic capacitors inside. But one capacitor we didn't account for was the so basically here it can show maybe, the parasitic capacitor at the input side, right? Because we sort of assume that we'll be driving with an ideal voltage source, so which means for pole calculations we are going to short it, so the capacitor is not going to play a role. But let us say I'm going to put this in some feedback like this. Right. Now even though you might be driving the input with an ideal voltage source here, now this parasitic capacitor will come into picture. Correct? So let's now see what might happen because of that. So which means because of this additional capacitance Cx, you will have an additional pole now. So which means your phase margin, do you think will be better or worse now? I have an additional pole, so phase margin, do you think will it improve or worsen? It will worsen, right? So of course, if you design it carefully, taking into account this additional pole, you will be able to design properly. But let's say you are sort of reckless and you didn't account for this, and then you find that this is basically causing you trouble. Let's see if we can do some patchwork to sort of get the required response. So maybe I'll throw the question back at you. So let us say you already designed this, you don't want to touch inside the OTA. Is there something that you can do here so that we can tackle the delay due to this additional capacitor? Think of it this way. Remember that this structure is the feedback network for the negative feedback system, right? So this is how it's right now. So R2, this is R1. Let's say the capacitor is not there. So the feedback is basically sensing the output voltage V1, and we get some voltage V2 fed back here. Right? So what is the feedback factor? So what is the transfer function from V1 to V2 here? R1 by R1 plus R2. So even if I plot it as a function of frequency, how is it going to look like? The magnitude? It's going to be constant. So now let us say this capacitor is now not negligible. So what will happen to the transfer function now? After some frequency, it's going to drop like this. And what is the pole location here? Again, for pole location, what do you do to the input? Ground it. So if I ground it, what is the pole location now? 1 by Cx into R1 parallel R2. Right? So at this point, it will start to roll off. Now the question is there something I can do so that at high frequencies I don't get this roll off, but hopefully it is constant or slightly higher, or it should not basically roll off drastically. Is there some suggestion that you have that we can do to this network so that the high frequency gain doesn't go to 0, right? Because at high frequencies, what is the gain now? At high frequencies, what can you say about the capacitor? So what is the gain from V1 to V2? At infinitely large frequencies, how much is it? 0. So I don't want this to be 0 at infinitely large frequencies, but I want this to be a finite number. So is there something that you can suggest we can do here? Okay, how do you add a 0? Why will that help? Another capacitor? I mean, where? Across R2. Okay, why is this good? Okay, he's suggesting we can add a capacitor across R2. Yeah, why do you think we can do this? I mean, why do you want to do this? Mm-hmm. Okay, now tell me, let's say add this capacitor, I will call the CY. At very, very high frequencies, what can you say about the transfer function from V1 to V2? At very high frequencies, among R1 and CX, which will dominate? CX is going to dominate. Similarly, here in this branch, which will dominate? So high frequency gain is dependent on what now? Ratio of? So what is that ratio now? Yeah, so this is basically CY by CY plus CX. Correct? Now depending on whether this ratio is greater than this or not, maybe, I don't know, you might have something like this or something like this. Correct? Now, in particular, let us say I choose, let me give an example. Let us say R2 is some K times R1. Right? So then if I choose my CY to be CX by K, what might happen? So what I'm saying is this resistor I have is basically K times R1. So now I go and put a capacitor here, and if I choose the capacitance value so that it is equal to the capacitance Cx by K, what will happen now? Okay, what happens to this ratio? What happens to this ratio first? 1 by? What happens to this ratio? 1 by K by 1 plus 1 by K. How much is that? So how will the transfer function look like in this case? Across frequencies, how will it look like? Yeah. So what's happening to the 0 now? Huh? No, 0. Yeah, the 0 is exactly cancelling the pole, so that here you had the pole. There is no confusion, right? Somewhere, right? Now we introduce the 0. That 0 will now exactly sit on top of the pole and cancel it, so that you don't have any frequency variation. This is again another example of the unobservable or uncontrollable state, where you have the pole 0 cancellation happen. So this way you can go and add a capacitance, and if you sort of choose it to be the sweet spot value, then this basically behaves like your old feedback network, where you just had only resistors. So that is one quick patchwork you can do to basically tackle the input parasitic capacitor. Again, the idea is you have a delay here. To counter the delay, you add a fast path through the capacitor. That's basically adding the 0. And that will make sure that, and if you choose a capacitance to be an appropriate value, then you can cancel the pole, so that the transfer function of the feedback network is constant across frequencies, which is what you would have had when you didn't have the capacitor here. Cool. Okay, any questions on this? Clear?